So here we are with lab number 8, and this is a really great experiment for you to do. We're talking about limiting reactants, and I think this will really help you study for exam 3, which is coming right up. Make sure that as you do this, you're really clear on your calculations and everything that's involved with limiting reactants. So in your lab manual, you're going to see 3 options for this experiment. You only have to do one. I'm going to demonstrate all 3, and I'm going to show the equations on the board and examples of the calculations as well. And I want to make sure that you follow along with this. It's really great. The advantage of the online course is that you can re-watch these videos as much as you need to. You can pause, you can follow along, you can repeat what I say over and over, and it's really great because that will help you to learn. So I think you're fortunate to have recordings of the class, because I know this is something in the in-person class I teach we always go over several times. So you have a recording to work with, and that's great. If you have more questions, there are the discussion board resources. You can use Ask the Class, or you can use the discussion board for the limiting reactant lab, and you can also always ask me through course messages. Okay, so the limiting reactant. The idea behind it is that in a chemical reaction, no matter how specific you try to be with mixing your reactants, oftentimes there's something left over. There's a little bit of something left over. And that's because one of the reactants ran out, so no more product can be created, and that other reactant is just going to be left in what we call excess. So it's advantageous for scientists to calculate ahead of time which reactant is going to run out first, so that we don't have a whole lot of leftover of the other reactant. It really depends on the reaction that we're carrying out, but some chemicals can be very expensive. They can be very toxic. We don't want leftover. And if you're working in industry, for example, on a large scale, this kind of calculation is really important because you could end up with tons, literally tons, of leftover chemical. So I'm going to show you how to do these calculations with examples of things that you can find in your kitchen. So the first example is making a peanut butter sandwich. It's no big deal if you end up with leftover peanut butter at the end, but this is an example for you to figure out how to calculate a limiting reactant. Okay, so our first reaction that we're going to do, I'm going to use, I believe in your lab book, it's just peanut butter and bread that you're going to use. I'm going to use 3 reactants here to show you an example of sort of a little bit more complicated reaction with limiting reactants. And I think it's good to demonstrate so that you can see how this one would work. So, for the sake of being a little bit different than what you're going to be using at home, so that we don't end up with the same exact numbers, instead of bread, like you have in your manual, I'm using English muffin, because I'm probably going to eat it afterwards, and I like that better than bread. And then I have peanut butter, just like in your lab, and I don't have any jelly, but I do have maple cream. So I'm going to use that, and actually that's locally made, so it's not labeled with grams per serving. So we're going to determine that in our lab, okay? So this is the making of a peanut butter and maple cream sandwich. Okay, so I'm going to start by writing the reaction on the board. So in this case, if we're using chemicals, we generally use the chemical symbols when we write reactions. Food doesn't have symbols necessarily, so we're just going to make them up. Also, if we're working with elements and compounds, we use molar mass in our stoichiometry concentrations. That's grams per mole. So we don't talk about food in terms of moles, because moles, as we know, is 6.022 times 10 to the 23rd. That's a huge quantity. And we talk about atoms and molecules in terms of that huge quantity because we can't see them. In order to be able to actually measure them, we have to measure them in groups of moles, groups of huge quantities. Something like bagels, you can see we measure in dozens. That's a similar grouping to a mole. What we're going to be using for these experiments are just serving sizes. So whatever's on the package as your serving size, you're going to use that because it's often indicated how many grams per serving size are in your package, and you can find that at the top of your container. You can see here, it will say grams per serving size, and the serving is 1 muffin, and this is 57 grams per muffin. So you're going to be checking all your packages for the mass per serving size, and that's what we're using in our calculations. So let's just make that clear first. Okay, so this reaction I'm going to use M for the symbol of the English muffin. And I'm going to use P as the symbol of peanut butter. And C as the symbol for maple cream. So the serving size on the package for the English muffins is 1 English muffin. The serving size for peanut butter is 2 tablespoons. And the serving size for maple cream is 1 tablespoon. So let's say that I really like maple cream just as much as I like peanut butter, and I want to actually use 2 tablespoons. That would be similar to using 2 moles. We can put a 2 in front of this because we're using 2 units, 2 serving sizes, 2 of those groupings. And we're looking at our food in terms of serving sizes. So we have a 1:1:2 ratio in terms of serving sizes in this equation. And it's a good idea to write those numbers that appear out front of your chemicals. You can write them above the reactants in your equation. That will help you when you're solving stoichiometry problems. I think that that's really helpful. So we don't have ones written out front because that's unnecessary. But to give myself an overview, I'm going to write 1, 1, 2. That shows a 1:1:2 ratio here. And our product is going to be MP C subscript 2, because both of those servings of maple cream are going to become part of this product, this compound, if you want to think about it chemically. So check to make sure the equation is balanced. It is balanced. You have 1 M, 1 P, and 2 C's on both sides. So what number would be out front here? It would be a 1. So we have a 1:1:2:1 ratio. So in other words, let's talk about this. If I have 1 muffin, I'm going to use 1 serving of peanut butter. It's a 1:1 ratio. Let's say I had 5 muffins. I would need 5 servings of peanut butter, 1:1. If I had 5 muffins, I would need 2 times that amount, 10 servings of maple cream, 1:2. That means you have to multiply by 2. So if I had 1 muffin, I use 2 tablespoons. 2 muffins, I use 4 tablespoons. And you can calculate in that way. If I have 1 muffin, there's a 1:1 ratio with the product. I can make 1 product. If I have 7 muffins, I can make 7 products. Let's look at this. If I have 2 servings of maple cream, I can make 1 muffin. It's a 2:1 ratio. You can always make half the number of product as the number of maple cream servings that you start with. So let's say that I start with 6 servings of maple cream. I can make 3 of these final products. So that's how we have to get our head around this equation. It's good to do that in any chemical reaction. Understand what you're looking at. Okay, so in this problem, I'll use the numbers that I give you in your lab manual. Let's say that I have 125 grams of, in your manual we're using red, here I'm using English muffin. I'm going to write the masses below each thing. Let's say that I have 50 grams of peanut butter and 50 grams of maple cream. Now, if we were using a chemical equation, the first step I would tell you is convert to moles. In this case, we're converting to servings. So I'm just going to write SER for servings. So to convert 125 grams of English muffin to the number of servings, let's set up our conversion factor. I'm going to write it right here. 125 grams. And we're using the equivalent statement that I showed you on the package. We're taking it right from the package. 1 serving equals 57 grams. So that would be 57 grams per serving. Or if you're thinking about chemicals, that would be the situation where we look on the periodic table and find grams per mole. So where do grams go? Would we write them on the top or on the bottom? The bottom, because we have grams here on the top, and we're looking to cancel them and determine the number of servings. So I'm going to write 57 grams, and when you write servings on top. So grams cancel, and we need to divide 125 divided by 57. We're going to probably just use 2 muffins. Now peanut butter, we're going to do that same conversion, 50 grams, and divide by the mass of peanut butter per serving. So our starting point, our starting measurement is 50 grams. And if I look at the container, we can see it weighs 32 grams per serving size, which is 2 tablespoons. So 32 grams per serving. So we have to do 50 divided by 32. And that gives us 1.56. So let's keep that measurement on the peanut butter is likely to the nearest gram. So I'm going to write a decimal there indicating we have 2 significant figures. So to keep 2 significant figures, we would have 1.6 servings of peanut butter. So you can be thinking in your head already, okay, if I have 2 muffins, how many servings of peanut butter would I need? If it's a 1-to-1 ratio, I would need 2 servings of peanut butter. This is close, but actually not quite there. So we already know that this is good. So we're setting out to find out which of these reactants is going to run out first. Which one is the limiting reactant? So when that reactant runs out, production of our product will stop. And whatever is left over is going to be considered in excess, and however much product we've made is going to be all that we're going to make. So let's start off just from the beginning of the equation. We have 2.2 servings of peanut butter. Sorry, of muffins. 2.2 servings of English muffins. So knowing that there's a 1-to-1 ratio of muffin to peanut butter, we know that if I have 2.2 servings of muffins, I would need 2.2 servings of peanut butter. Do I have enough? No, I don't quite have 2.2 servings. So this is going to run out before the muffins do. But is this going to run out before the cream does? Let's find out. Well, let's first compare the muffins to the cream and check to make sure that the muffins won't run out before the cream. So that is a 1-to-2 ratio. If I had 1 muffin, I would need 2 tablespoons of cream. Sorry, 2 servings of cream. 1 serving of muffin, 2 servings of cream. That's twice as many. So if I have 2.2 servings of muffin, I would need twice as many servings of cream. Is 2.4 what we have? Is that twice as big as 2.2? No. So that's actually going to run out also before our muffins do. So both of these are running out. Now which one runs out first? We have to compare them to each other. So let's look at the peanut butter. I always start from the beginning of the equation. To me that makes sense. I compare it to each one. You may find you have your own approach, but we're looking at the relationships between each reactant. So now, peanut butter. We have a 1-to-2 ratio, peanut butter to cream. So for every 1 serving of peanut butter, I need 2 servings of cream. So if I have 1.6 servings of peanut butter, I need twice as many servings of cream. Is 2.4 twice as big as 1.6? It's actually not quite. And I'll show you how to write that out to double check yourself. This is, if you're doing this on an exam, I want to see most of these calculations written out. That way I can check how your thought process is going. So I have 1.6 servings of the peanut butter. I'll write that as 1.6p. And our conversion factor comes right out of the equation. So I'm going to do 1p on the bottom. I don't need to write the 1. And 2c on the top. How do I know to put the p on the bottom? Because we're trying to move from servings of peanut butter to servings of cream. We're trying to figure out how many we need. So that would be 1.6 times 2, which makes 3.2 servings of cream. That's how much we need. We need 3.2 servings of cream if we were to use all of this peanut butter, but we only have 2.4. So that's actually going to run out before the peanut butter does. So this is in excess. this is going to run out before the muffins, but there's still going to be some left over as compared to the cream. So we've actually just figured out that this is our limiting reactant. And we can double check this by saying, well, what if I did use up all the cream? How much peanut butter would I need? And do I have enough? So let's find out. If I have 2.4 servings of cream, I'm going to write 2.4C. And then just take right out of the equation. I'll put 2C on the bottom. That's what I'm trying to cancel. And I'll put 1P on top. C's cancel. 2.4 divided by 2 is 1.2 servings of peanut butter. You could do that one in your head as well. It's a 2-to-1 ratio. You need twice as much cream as peanut butter. If I have 2.4, this better be twice as big as the peanut butter if I'm going to have enough. So if I have 2.4, I would need 1.2, that's half. I need 1.2. Do I have 1.2? Yep, I have 1.6. So this actually is not going to run out at the same time as the cream or before the cream. It's in excess as compared to the cream. So this is going to run out very first, and that's called our limiting reactant. Because once the maple cream runs out, that's it. We can't make this wonderful snack. We can make something else, which is peanut butter and muffins. But we can't make this MPC2 because we've run out of the cream. Okay, so now from here, we can determine how many servings of the final product we can actually make. So it's a 2-to-1 ratio. Let me just make sure that you can see. It's a 2-to-1 ratio for the cream to the product. And we know that our product is based on the limiting reactant. As soon as this runs out, any product that we've made is all we're going to have. So to find out your product, you have to look at the limiting reactant and the limiting reactant only. So for a 2-to-1 ratio, if I had 2 servings of cream, I can make 1 serving of my snack. So it's twice as big. 2.4 is twice as big as 1.2. So I can make 1.2 servings of my snack. And you could write that out as a conversion factor as well if you like. 2.4 of cream. And I know 2C for every 1 MPC2. I'm going to write 2C on the bottom and my product on top. C's cancel. So 2.4 divided by 2 is where I got that 1.2 from. So that's how many servings I can make. Now, also useful is to find out exactly how much is left over of your other 2 reactants. So let's look at that. We have a 2-to-1 ratio with each of the other reactants. So this is simple. Just like here, 2-to-1, I have 2.4 servings. I'm going to make 1.2 servings once that runs out. In the other 2, I have 2.4 servings of cream. I'm going to use all of that because it's going to run out. So how much am I actually going to use of the other 2? Well, it's a 2-to-1 ratio, so I'm going to use half. 2.4 servings of cream, I'm going to end up using 1.2 servings of peanut butter. Half as much. If I use that much, I can subtract and find out that I'm going to end up with 0.4 servings of peanut butter left over, which we know from the container a serving of peanut butter is 2 tablespoons. So we're going to end up with close to 1 tablespoon in excess. And when we make our snack, we're going to find out if that's true. Same thing with the muffins. Let's write this out like a conversion factor so that you can see. If you're not doing it in your head, you can always write it on paper. So if I'm starting with always my limiting reactant is what determines this. 2.4 servings of cream. I'm trying to find out how much I'm actually going to use of my muffins that I know are in excess. So we have a 2-to-1 ratio. The 2 goes on the bottom, 2C. And the 1M goes on top. C's cancel. That's where I'm getting this idea of dividing by 2. I have 1.2 muffins. It's how much I'm actually going to use. I'm actually going to use 1.2 muffins. And I'll end up with 1 serving of muffin in excess. So actually, if our calculations are right, we have enough food here to make 1.2 of our very good snack, and then we have 1 muffin and 1 tablespoon of peanut butter left over, which I'm sure we can figure out what to do with that. So now, if you want to take it one step further, this isn't required for your lab report, but it's oftentimes what's asked of you in a stoichiometry question. So what would our final product weigh? Well, we need to know how much one serving of our product weighs, and we're going to multiply that by the number of servings we have. Let's say that our product weighs 200 grams, as an example, per serving, and let's say I have 2 servings of it. We know that I would have 400 grams there. So let's find out in reality what our product weighs. So we know the muffin, the M, weighs 57 grams. That's from the package. We know that the peanut butter from the package weighs 32 grams per serving. And we found out that the maple cream weighed 21 grams per serving, and we use 2 of them. There are 2 C's in that compound, so 2 times 21. And we can add that up, just like you would if you were looking at the periodic table for grams per mole, and adding them all up in a compound to find out its molar mass. So we have 131 grams, 131 grams per serving. Okay, so knowing that we have 131 grams per serving, and we have 1.2 servings, we're going to multiply the mass by how many servings we have. So let's show that as a conversion factor. I have 131 grams, and I have, well, actually, what I should do is write it this way, our measurement times the conversion factor. So I have 1.2 servings, and I know that each serving weighs 131 grams. So that turns into, servings cancel, 1.2 times 131. You end up with 157.2 grams. So actually, this lab is a good opportunity if you would like to practice percent yield. When you make your final product, whichever experiment you do, you can weigh it. You can find out, do I get the same exact mass as I calculated? Because this is now, we can consider it our theoretical yield. We did all this math, and we found out that in theory, I should be making 157.2 grams of my product. Now in reality, you're going to find out, very similar to what happens in chemistry lab, the product that you make is not always what you predict you're going to make. So you may actually end up making something that weighs 140 grams or 170 grams. Then you can say what percentage of what you expected did you actually make. It could be 80%, could be 120%. You can calculate that. And this percent yield is something that's included in the chapter that we're studying. And it will be on the test. So if you want to try it out at home, you can. It's a simple calculation. And if we have time, we'll do that here as well. Okay, so next we're going to make our snack. And we're going to find out, did we calculate this right? Is our cream going to run out first? Are we going to have a tablespoon of peanut butter and a muffin left over? So let's get to that. Okay, so here we are. We're ready to put our calculations to the test and see if we come out with the same results in person. So the first thing I'm going to weigh is the 50 grams of peanut butter and of maple cream. This is the information you were given to set out on this limiting reactant quest. So we're going to, I have a small container, I put it on my digital scale. I'm going to 0 it. So that now the scale is saying there's nothing here. When I add any maple cream, it's going to measure that and only that. So let's get this out of the way. We need to measure 50 grams of the maple cream and 50 grams of the peanut butter. So I know that 1 tablespoon weighed about 21 grams, so that gives me an idea of how heavy this is. I'm scooping kind of a large portion at once because I know, right, that's 23 grams. trying to get up to 50. It's 32, 45, 46, 50, 51 grams, 50 grams. Okay, we have 50 grams of maple cream here. So this is what we were given for our experiment. Now I'm going to measure the peanut butter. Now this will be a new container, so we have to again zero the scale. Surprisingly, that container was heavier than this big bowl. So I'm going to zero the scale. And then measure 50 grams of peanut butter because, again, this is the starting material we were told that we have. So, $30 grams. Looks like it'll be too much. 79 grams, so I have to take some away. It's good to measure in little increments so that you don't end up having to take some back. That's a skill that you'll definitely find out if you work in the chemistry lab. You don't want to be taking powder away from your sample dish and trying to put it back in your container because of contamination. At home, as long as you know that your utensils are clean, you don't have to worry as much. But putting it back into the container in the lab is a no-no, so you want to measure very carefully, adding a little at a time, not having to actually take it away. So I'm still at 60 grams and I'm taking away 55 grams, 54, 51, 50 grams. Okay, so now we have 50 grams of peanut butter. And I'll set that aside. And the next thing we need to weigh out is our muffin. So they tell us we have 125 grams of English muffin. And I can put that right on the scale. Well, I'll put it on a plate. Okay, so I'll put the plate here, hit 0. Okay, so now, and if you're using a digital scale, make sure that you're in the right mode. This can read grams, it can also read ounces or pounds, so make sure that you're seeing grams on the screen. Alright, so they say a muffin weighs 57 grams, let's find out. 56 grams, that's pretty good. They were pretty accurate. Now we'll add a second muffin. That's 112. And they say we have 125 grams, so let's just follow the directions exactly. I'm going to take some more muffin and add it to my plate. $122, $124, $126, 125 grams. Okay, so we have 125 grams of muffin, and 50 grams of maple cream, 50 grams of peanut butter. And let's do our preparation. So we have everything that we started with. Just make sure you can see. We have everything that we were told we're starting with. Now, we know that for every one muffin, and I know I'm not probably going to use these scraps, but for every one muffin, I'm going to use 1 serving of peanut butter, which is 2 tablespoons. So I'll be measuring out 2 tablespoons and putting it with this muffin. Okay, so I've cut the muffin in half. So for every one muffin, we're using 2 tablespoons of peanut butter. Alright, so we need 2 tablespoons of peanut butter. That's 1 serving. So I'm measuring that out. 1 tablespoon, and I'll put that right on my English muffin. Consider that a product. We're working on making our first product in our reaction. And then I have a second tablespoon. Okay, and put that on the English muffin. Now, percent yield, we were talking about percent yield. Oftentimes in the kitchen and in the chemistry lab, the reason we come out with less than we expect because we lose some of our reactant to the materials that we're working with, the instruments that we use to carry the materials and whatnot. So some of this peanut butter is staying on the spoon. I know this is going to weigh a little bit less than 131 grams because of that. Very, very slightly less, but that's the case. Okay, so now the next thing that we need is our 2 servings of maple cream. 1:1:2 ratio, 2 servings of maple cream. And we know that the maple cream, 1 serving is 1 tablespoon. So I'm going to use my tablespoon again and measure. Now for the peanut butter, 1 serving was 2 tablespoons. That's what it said on the box. And for the maple cream, 1 serving is 1 tablespoon. That's what it said on that box. So we're going to use 2 tablespoons of maple cream because that is 2 servings. And we're following our equation for the perfect snack. So we're going to take 1 tablespoon of maple cream and put it here. And 2 tablespoons of maple cream. I can already see this is going to run out quick because I had to scoop around for that second tablespoon. There is a little bit more there. Okay, 2 tablespoons. Now, this snack has a lot of maple cream and a lot of peanut butter on it. Oh my goodness. But that was the formula, and we're following it. Okay, so we have 1 product. We'll find out how much this weighs in the end. Now, we predicted that we could make 1.2 servings. We made 1 serving, and let's see. I'm trying to figure out how to do this neatly. We have 2.2 servings of muffin. That's how much we measured out. You can see we have these 2 muffins and then the pieces. Interestingly, the way we calculated it, they said we could make 1.2 servings of our product, and that the maple cream would run out. So we can assume, we also were thinking that we would have 0.4 servings of peanut butter left over. So we really have to do some calculating, figuring how much peanut butter we need to use for 0.2 servings of muffin. But we can do that. If I have 0.2 of a muffin, I would need 0.2 servings of peanut butter. So what is 0.2 of 2 tablespoons? It's 0.4 tablespoons. So I would take 0.4 tablespoons and put it, I'm just going to eyeball this for the sake of example. I know that, well, I can see kind of what I have here. I'm going to take about half a tablespoon and put it here with my 0.2 of a muffin. And then, so this is going to affect our percent yield as well. This is human error. This is human error. Because I don't have a measuring device to measure 0.4 of a tablespoon, and I don't want to get that involved with this experiment, mostly putting it together and understanding what ran out and what didn't. Okay, so the 1:2 ratio, if we have 0.2 left of a muffin, and we want to use 0.4 tablespoons of maple cream, let's see how much maple cream, if it's close to a half a tablespoon, that'll confirm for us that it would run out. That's kind of the important thing, is does this run out? So if you can see, I'm scooping all the maple cream up, and it is making about half a tablespoon. So we used up all our maple cream. Maple cream is a limiting reactant. We used it all up. And left over, like we calculated, We have 1 serving of muffin left over, 1 serving in excess. .2 servings of our snack. So I'm going to just take this excess muffin off the plate and weigh what we came up with and figure out if it's similar to what we were expecting. Now actually, I would have to re-tear the plate. So I'm going to just take out another plate. A bowl, actually. That's what I had. And I'm going to tear it, meaning push 0, so that it is only going to measure our product. And I'm just going to put everything in this bowl. So we have our 1.2 of our product. Now let's find out what it weighs. I'm curious. Okay. 143 grams. That's to be expected. So we did lose some mass along the way. We probably lost some peanut butter on the measuring spoons. We've got a little bit of crumbs over here, and we definitely eyeballed that 0.4 of a tablespoon for the peanut butter. So 143 grams. That's what we came out with. And that's ballpark in the range of what we expected to get. So what we finally created was 143 grams of our product. We made 1.2 servings of our product that I'm going to eat. And now we can actually calculate percent yield with that. Now to find percent yield, this was not included as a requirement in your lab, but it's a great demonstration and it's a great opportunity to show you what actually happens in real life in the lab or in the kitchen because of human error. So it's very similar. Working in the kitchen is very similar to working in the lab because we've got some materials we're working with. We have to transfer them from one container to another using some kind of utensil or measuring tool. And inevitably some of the sample is lost along the way. So oftentimes it's more likely for percent yield to be less than 100 than it is to be more than 100, and that's because of material loss along the way. Percent yield can be more than 100, and what that would mean is maybe something else was added to the mix along the way, or maybe the measuring wasn't done accurately, something was over measured. So calculating percent yield is a great addition to this lab, so I'm going to show you. It's not complicated. So percent yield is your actual mass over your theoretical mass times 100 to make it into a percent. So basically, here this was our actual mass, 143. We're going to put our actual mass over our theoretical mass and multiply by 100 to give us a percent. So in this case, our actual mass was 143 grams. And our theoretical mass, after all that calculating we did, we figured we're probably going to get 157.2 grams of our product. All right, so let's figure out what percentage that is. I'm kind of impressed we were pretty close to what we were expecting. Let's find out what percentage that comes out to be. .909, and then multiply it by 100, we have 90.97. So how many significant figures should we keep? This has 3, this has 4. So we're going to keep 3 significant figures. So this is an interesting rounding problem. We have 90.97. And if we want to keep 3 significant figures, we'll look at that 7. That will bump the 9 up to a 10, which will give us 91. And we still want 3 significant figures, so we're going to say 91.0. Okay, so even with all of that sample loss, the peanut butter at the spoon, and the eyeballing that 0.4 tablespoons of peanut butter at the end, we came out with a 91% yield. So we created 91% of the product we expected to create. This is the type of calculation that's important to do if you're using chemicals that are expensive or that are pollutants that you don't want to have left over in excess, you want to calculate how much you're expecting to create. You want to know the percent yield for the type of reaction you're doing. And you also want to know how much of each thing will be left over with the starting material you're expecting to use, and then you may modify how much starting material you need to purchase. Like for example, I know now that with 125 grams of muffin as starting material, I end up with one whole muffin left over. So in the future, if I were to do this, I would take 57 grams away. That's how much one muffin weighs. And I would start with less than that. I would start with something closer to how much muffin I'm going to end up with at the end. So these calculations ahead of time can help predict what your final product will turn out to be and can help you more efficiently use resources. Obviously in the kitchen, it's not a huge deal if we have a little bit of leftover food, but in the chemistry lab, these types of calculations are very important because of the materials we're using. Okay, and that's an example of a limiting reactant experiment along with your calculations. And if you have questions, feel free to use the discussion boards or use course messages to ask. And make sure that you upload your calculations onto Blackboard so I can check them over, as well as a picture or a video of yourself doing your experiment.